Welcome back to another Explainer. I am so thrilled you're joining me today because we are looking at a truly fascinating chemistry mystery. We're talking about how things mix, how they separate, and the secret rules that molecules follow without us even realizing it. I mean, have you ever noticed how some liquids just seem to have a mind of their own? Well, today we're going to unpack exactly why that happens. Okay, let's dive into this.
I want you to picture something in your mind, or maybe you've even done this at home in your kitchen. Imagine a clear glass jar. You pour in some water, and then you pour in some cooking oil. Finally, you squeeze a single dark drop of food coloring right into the middle of the jar. What actually happens? Does the whole thing turn into one big murky puddle? Does the color shoot to the top, sink to the bottom, or just hang out somewhere in between? This isn't just some fun visual trick. It's a puzzle that reveals a fundamental law of nature. And to solve it, we need to understand exactly who's involved in this chemical dance.
First up, Section 1, the cast of characters. We've got to meet our molecular actors.
To figure out this mystery, we first need to meet our main actors. Character number 1 is the solvent. Now, the absolute best way to think about a solvent is to imagine a gigantic, welcoming room. It's a liquid that has plenty of space and capability to allow other substances to just come inside and hang out. Water is actually the most famous solvent in the world. It's kind of like this massive banquet hall that welcomes almost everyone. So, whenever you hear the word solvent, just think of the host or the room providing the space.
Right, so if the solvent is the room, our second character is the solute. The solute is our special guest arriving at the party. This is the substance like salt, sugar, or, like in our earlier example, that drop of food coloring that's looking for a room to stay in. When the solute walks into the solvent room, it unpacks its bags, spreads out, and mingles perfectly. Basically, it gets completely dissolved.
Moving on to Section 2, the unmixables, also known as immiscible solvents.
Okay, so we know that a guest needs a room. But what happens when we have two different rooms, two different solvents that absolutely refuse to share the same space or be in the same building together? Well, in chemistry, we call these stubbornly uncooperative liquids immiscible. Immiscible liquids are like fierce rivals. You can put them in the exact same jar, you can even shake that jar as hard as humanly possible to try and force them to get along. But the literal second you stop shaking, they will immediately separate themselves right back out, forming distinct, stacked layers. They physically draw a boundary line between each other, basically declaring, this is my side and that is your side. Oil and water are the classic immiscible rivals here.
Think about mixing water and fruit juice. They happily blend together into one uniform, tasty drink, right? They cooperate. They're miscible. But our immiscible liquids, like water and oil, sit entirely apart, creating a strict line in the sand. And you know that visible line dividing the two layers? That is the battlefield for the